Thank you, Roy. Hi, everyone. Very happy to be here or virtually here. And thanks everyone for coming back from the coffee break, not getting lost in Gather Town. So thank you, especially for those who stayed up late or woke up early to watch this talk. So before I dive into the subject of high contrast imaging and background subtraction, so I'm going to try to convince you that some of the technique that we have developed in high contrast imaging can be used also in the mid-infrared. But before I dive into that, I would like just to take a step back and show you a couple of slides about where we are at today in terms of exoplanet imaging. And so I like to start with this, now very famous plots showing the population of planets that have been detected as a function of separation in the x-axis and the planet mass in the y-axis. So the point I want to make here is that, direct imaging, as you can see, is really enabling to explore a part of the parameter space that cannot be explored with any other technique. And I also want to stress that we are today in a very interesting period of time where the parameter space that is explored by radial velocities and direct imaging starts to collide. And actually, last week was announced the first follow-up by direct imaging of an RV planet, which was actually, in this case, followed up with infrared interferometry, which is another way to do direct imaging. So very interesting time right now. I cannot resist showing this plot as well, which is really, this video, which is really, I think, mind-boggling. Still, when I see this and I think about how much instrumentation development have been needed to provide this kind of videos and what this actually represents, that is the Keplerian motion of planets around a star that is 40 parsecs away. This is, this really blows my mind. Well, that shows you a little bit where we're at today. So direct imaging allows us to follow the orbital motion of planets right now, which gives us access to things like the architecture of planetary systems, also informs us about their formation and other things. And if you want to go further, of course, you have to use spectroscopy, and this is what is done now by specialized instruments, like, for instance, the Gemini Planet Imager, GPI here, showing these spectra in the top plot at Y, J, and H band, and here for the same planet, beta pictoris B, the spectrum that has been obtained this year with gravity infrared interferometer at the VLT. Showing the exquisite precision that can now be achieved with this kind of measurements. For instance, you see here very nicely the CO lines and all these information that we can collect using spectroscopic capabilities inform us about the physical properties of planets, like effective temperature, surface gravity, but also now with this exquisite precision, information about the C2O ratio or the metallicity of the planets as well, which give, once again, direct insight into their formation process. So this has already been shown. So I think, especially in the thermal infrared, we can now access the formation scenarios directly by looking at protoplanetary disks and looking for the signs of planet formation, which can be the presence of spiral arms or gaps or other irregularities in the disk, but also now being able to look to directly witness the formation of the planets inside these disks, which is really very important to constrain the formation models for these planets. And so, as Cora already mentioned, there is a very good reason for going to the thermal infrared when observing directly extrasolar planets. This is because of the contrast, so there's a flux ratio between the planet and the star that can be more favorable in the infrared, especially when you go to older planets, like is shown here. So if you go to the 5 gigayear planets, there is absolutely no chance for you to detect that in the near infrared using the current instrumentation. While if you go to the mid infrared, you have a chance to do so. And I also wanted to mention, on top of what Cora already mentioned in terms of incentive to do thermal infrared, it's also the presence of specific molecules. Some of them have all other footprints in the near infrared or in the visible, but there are some of them that are very unique to the thermal infrared domain. So now let's move on to the topic of today. And so I want to explain a little bit what is the challenge of detecting exoplanets with direct imaging, and try to connect that with the challenge of removing the background in medium infrared observations. And so on the left, you see, I mean, the kind of typical raw data that we can get with a high contrast imaging instrument. And you see all these speckles that actually evolve over time at all time scales. So we have the atmosphere that is varying at a very short time scale, but you also have the instrument following the object on the sky that deforms, that has a thermal relaxation, mechanical relaxation that leads to variations in the aberrations inside the instrument. And so that creates speckles varying at different time scales, just like is illustrated on a video on the right. So the rapid variations will generally average out to some level, while the quasi-static structures will not, and are usually the most important nuisance to the exoplanet imaging instruments. So a technique that was developed in the last decade that has really revolutionized the field of direct imaging is angular differential imaging. And so it basically boils down to keeping the pupil stabilized, so using pupil tracking instead of field tracking, while observing a specific star in the sky to look for planets around it. And so the idea is that by keeping the pupil stabilized with respect to the detector, is that all the quasi-static features that are generally associated with the pupil, so basically related to aberrations or diffraction inside the pupil, they will stay fixed on your detector, while the field, due to the Earth rotation, will rotate around the optical axis of your telescope, which is usually coincide with a star that you want to explore, well, of the neighborhood of which you want to explore. And so by creating this diversity between what is the true astrophysical signal and the speckles, you have a lever to distinguish between the two contributions. And so this is the typical way that we use this diversity in order to detect extrasolar planets. So on the left, you see basically a series of images over time where the star has been centered on the optical axis, and you see that the field is rotating. So there is a mock planet here in red, showing that this planet is rotating around the star at a known rotation speed, because it's just related to the rotation of the sky above your telescope. And so if you take the median of all these images, what you capture is all the features that are static or quasi-static in the image, while a planet, if it has moved by enough pixels over the time your observing sequence is obtained, will not show up in the median. So then you can remove this median from each individual frame in your data cube, and you are left with what is shown in the third column. I don't know if you can see my pointer, but anyway, you see that we have removed a large part of the stellar PSF and all the speckles that are quasi-statics in this stellar PSF, and we are basically enhancing the contrast between the planet and the star residuals. After that, you just derotate your sequence to make sure that the planet is at the same position in all the frames before you combine all the frames together using a median or a mean to obtain your final image. And in that way, you basically recover all the signal of the planet at a single location. So you basically get the same SNR as if you were, in terms of, number of photons that you get is the same as if you were using field tracking, except that now you have been able to remove a large part of the stellar signal thanks to this pupil stabilized observations. Okay, so this is just a little part of the whole high contrast imaging post-processing pipeline, which goes from the basic calibration and cosmetics of on the raw data to the detection. And so what I'm going to talk about is today is just this part where we try to remove as much as possible the stellar PSF in order to enhance the contrast between the planet and the star. I'm not going to talk about the detection part. So, well, I've showed you a very simple way to use the data and the diversity in the data, but there are more advanced ways, and one of the mainstream ways of doing that today is to use PCA, principal component analysis. And so the first thing you have to do before you use PCA is to turn your 3D data cube into a 2D matrix. And so, well, basically what you do is just you take your cube, you stretch the images to get vectors instead, and so you reform your 3D cube into a 2D matrix on which you can then apply standard mathematical tools like singular value decomposition, and that's the basis for PCA. So when you use singular value decomposition, you basically get eigenvectors, which are in this case eigenimages. And this can be also called principal components. And so these principal components are ordered by the quantity of information they have or they reproduce from your sequence. So the first few principal components will contain most of the signal that is quasi-static or quasi-static in your images, while the higher principal component will capture features that are more transitory in your images. And so what you expect with principal component analysis is that the features that are quasi-statics will be in these first few principal components, and you can then truncate your basis to these first few principal components. And you hope that the planetary signal will not be captured by them. So once you truncate your basis, so you keep the first few eigenvectors, you can project each image of your cube onto this subspace. So you have basically defined a subspace of your big matrix that is a low-rank subspace on which you can project your images. And when you project these images, the things that are quasi-static will project onto these and will be captured by this projection, while the things that are transitory will generally not project well in this basis, which only capture the static features. And so that's what is shown here. So basically, you use the whole information that you have to compute this low-rank subspace. You project each of the images individually onto that low-rank subspace to provide an estimation of your PSF. You subtract it from each frame one by one to get the residuals, and then once again you derotate and you min combine or median combine these residuals. So this is the way. I mean, there are of course variants to this technique, but this is the way high contrast imaging data are processed generally nowadays. So where do we go from here? So on the left, this is my background. This is the background that I'm used to tackle, and on the right, this is the background that a mid-infrared astronomer will generally be trying to remove. So what can we do? So I think there are two main things that can be learned from the high contrast imaging community. The first one is that pupil tracking helps. So if you manage to stabilize the pupil, that will allow you to make a lot of these quasi-static background structure fixed, because a lot of them are attached to the telescope pupil itself. So this is something that Bernard already mentioned earlier today. So basically, these features will not move, and you will be able, once again, to try to disentangle between the non-moving and moving features if you are just looking at how the objects move in the field. Another advantage is that pupil tracking, because it stabilizes the pupil, allows you to easily mask the spiders, which is usually not done. I mean, if you track the field, you cannot mask the spider, because then you would need to have a rotating mask called mask immune instrument, which is usually not the case. So in In this configuration, you can remove more efficiently the thermal emission from the telescope structure itself. Also, because mid-infrared observations use short exposures, usually the field rotation is not a problem because the exposures are short enough for the field not to move too much to lead to smearing. So I think it is probably good practice for a lot of mid-infrared instruments to try to generalize this use of pupil tracking, which is usually not a major effort as long as you have access to a derotator that can be addressed to follow the pupil instead of following the field. So a second important thing that we can learn from high contrast imaging is that these low rank approximation can really be useful in removing static or quasi-static features in the images. So this is most appropriate for point sources, and actually it's known to affect. So if you use this this technique where you let the pupil fix and the field rotates, and you use low rank approximation to remove the fixed background, this is known to affect the image, especially of extended sources. And actually, there are two main ways this can be explained. On one hand, part of the sources themselves, so the sources of intel will be captured by the low rank approximation, and so they will project onto themselves and be subtracted partially during the PSF subtraction in high contrast imaging or the background subtraction in mid-infrared astronomy. And there is also the phenomenon of over subtraction, where the source projects in a non-zero way onto the low rank subspace, just because some speckles have a shape that or the background has a shape that matches the shape of the source that you are looking for. So in the case of mid-infrared observations, there are possible solutions to mitigate these two problems. So one of them is that if you know that your source is compact, you can just mask the location where the source is supposed to be placed and compute your low rank approximation on the out parts of the of your image, where you know that the source is not present. That will basically remove the self-subtraction phenomenon. And it's also more straightforward to apply these kind of techniques when you have access to dedicated background measurements, in which case, once again, self-subtraction can be removed because you do not have the source present in these dedicated background measurement which basically target an empty region of the sky. So now I'm going to use a very nice illustration from the paper by Hunziker et al. 2 years ago that nicely described the use of PCA for background subtraction. And so I'm going to show you the steps that we take to do that. So on the left, you have the raw data with all the nasty features that you can see in mid-infrared background images. So these are NACO M-band images at the VLT, and you see that there is a source in red somewhere in the field. So first you subtract the mean, and you get something that is already much cleaner. I mean, the mean of all the images in your cube, of course. But if you change the cuts, you see that there is still a lot of structures present in the background. This is at the bottom right. And you would like to get rid of these structures, of course. And so what you do in this case, in these specific observations, where dedicated background images were obtained during the observing sequence, so that can be with chopping or just by dithering the star back and forth in different positions on your infrared detector. So you use these dedicated background images, and you compute your principal component analysis. So basically, you do singular value decomposition on the library of background images that you have, and you look at what the the principal component looks like. And so this once again illustrates that the principal components are ordered by increasing contribution to the representation of your background. So the first component captures the structures that are mostly common to all the frames. The second component captures things that start to be slightly different from one frame to the other, and then you go to higher and higher number of principal components, capturing more and more subtle features that appear generally at higher spatial frequencies as well.
Olivier, you
yes?
have 4 more minutes.
4?
4 more minutes.
Okay, good. And so this is what you do. So you have the image that I showed before with the background that is non-uniform. You project that onto a series of principal components. You can choose how many you use depending on how well you want to reproduce the background. In this case, it has been projected onto the first 60 principal components and then added to create this representation of the background, which you subtract from the initial image to get your residuals. And so, well, this is basically a generalization of what we have been doing in the high contrast imaging community to the case of the infrared background. And these kind of techniques are available in specific packages like VIP and Pinpoint that are available on GitHub. And so I just wanted to mention that the position of the star, of the object of interest, has been masked out so that it doesn't contribute to the computation of the coefficients of your lower rank approximation. So when you project onto your lower rank subspace, you only project the parts that are outside the location of the source. Okay, and so this is just to show you how the representation of the background evolves as a function of the number of principal components you use. The more components you use, the higher the fidelity in the way you reproduce the background. Okay, and so I just want to show 2 last slides before concluding to show you that, I mean, we can even go beyond PCA. So in the field of high contrast imaging, there have been more advanced algorithms that have been proposed. Usually these algorithms are more geared towards detecting specific features. Like for instance, in the case of match filtering, you look, or maximum likelihood, you look for a specific feature, generally of a point source. So it might or might not be useful for mid-infrared astronomy in general. There are other kind of techniques like morphological component analysis that can look for other kind of features. If you manage to find a basis where the signal you are looking for becomes sparse, well, in this case, in the case of this paper by Benoît Perret, he has used a base of shearlets to express the image of a circumstellar disk in a sparse method, in a sparse manner. And then you can apply mathematical tools to separate the signal from the noise once again. Deep learning is also starting to be used in the community, and it could also be used in the case of mid-infrared astronomy by learning the background structure using a large library of background images. The good thing is that there are now pre-trained networks that are available off the shelf that you can directly use to train on your specific object of interest. And so finally, I also wanted to mention that background subtraction is also studied in the field of computer vision. And actually, this is a very, very vast literature. And I think there are some things that we can also learn from this field. So I want to point towards this review by Thierry Boumans in 2014, where you can see there is a long list of techniques that are used to model the background in video sequences. Of course, the problem is a little bit different because in this case, we're trying to identify a foreground on top of a background, and the foreground usually completely masks the background, so you don't have the addition of the light from the background and the foreground. But still, the way you model the background has some common features with our field. In particular, we have been trying robust PCA methods in the field of high contrast imaging with some success, and so you might want to check that out. And so, yeah, I just want to leave you with my 2 take-home message. Pupil tracking is your friend. You should look at it. might improve your observations. And lower rank approximation is also looks like a promising way to model and subtract the background residuals. Thank you.
Many thanks, Olivier, for this very nice talk. So let me see, there are no raised hands yet. I'm looking at the Slack channel. There's a question by Mario van den Anker. What complications do you foresee in background subtraction for IFU data in METIS?
Well, I must admit I have not given too many thoughts about that. Maybe Leo has, has thought a little bit more about that. I've only thought about the high contrast imaging part of the IFU, and indeed there are some complications related to the fact, I mean, that the sampling is not, I mean, in terms of pixel size, is not as good as in the imaging camera, and also because I mean, if you wanna use some dithering methods, you are also kind of limited by the way you do the high contrast imaging. If you have a focal plane mask, you cannot move the star around to do dithering, and that can also be a problem when trying to subtract the background in IFU images.
Okay, thank you. There's a question by Thane Curry. He asks, how does a PCA-based approach compare to a full rank least square subtraction, such as Loki, in terms of background RMS?
Okay, so I don't know if the question pertains to high contrast imaging or background subtraction. I would assume that it relates to background subtraction. So I know that Loki has already been has also been applied to background subtraction. So there is this paper by Raphaël Galichet, I think in 2011. Yeah, I must admit that I have not looked into a comparison, but my assumption is that it should fare quite in a similar way, because as you can see, when you use PCA for background subtraction, usually you go to a relatively high number of principal components, which basically brings you close to a full rank approximation. So I'm not sure what is the added value of taking the extra few principal components. I guess they would mostly add noise rather than allow you to subtract the background. So I think that it still makes sense to truncate your basis in order to try to reduce the amount of noise. But yeah, I have no quantitative estimation of that.
Okay, we have time for one more question by Ryan Lau, who asks whether the PCA-based background subtraction methods have been applied in N or Q band.
Not that I know of. No, I don't know. Sorry.